Hey, today we're going to do a thing about circuits. It's going to be mostly review for you guys since you did this in your AP1, but so we'll go kind of quick with a little bit of new stuff about Kirchhoff laws if you have more than one battery and so on. We'll get to that in a moment. So you notice it is the C. There'll be a teeny tiny bit of calculus in this, but not a lot. So, excuse me. So a reminder, potential difference, that's just measured in voltage, and that's the electromotive force. Okay? So batteries have an electromotive force. There's a chemical reaction that happens that pushes electrons through there. You have this is 1.5 volts higher on one side than the other. Technically, that would be like a negative 1.5, and that would be a 0. The potential difference is 1.5, and so on. So a lot of times they call EMF the electromotive force, which is the potential difference you get across the battery when it's not hooked up to any kind of a circuit whatsoever. Okay, so for the most part, that's not an epsilon. That's not the epsilon that we use with capacitors and whatnot. This is actually should be a little bit larger. This should be the same size as that. It's called electromotive force. That's measuring a potential difference. Okay, alrighty. So basic circuit, you got your battery, you got your light bulb, and there you go, you got a source. Alrighty. So we're talking about stuff moving. What's a flow of charges through here, similar to a flow of water. So as if this is a water pump, you'd also have to have a hose coming back out of this bucket that goes back into the pump. They kind of missed that tube there. Because what the pump is it pushes the water one way, but it has to push back into a tube, then this circulates it around through the tube, same as what a battery does. So the potential difference is like the pressure difference that moves the water from one spot to another. The electromotive force or voltage is electromotive force, the electric pressure that pushes the charges around in the circuit that creates a current or a flow of charges. So the calculus way, it's the change in charge per change in time. So it is dq per dt, but that's just your flow of charge in coulombs per second. Okay? So there's a lot of electrons are actually flowing. So we don't use electrons per second. We actually use coulombs per second. And by convention, we don't actually talk about electrons moving. We talk about a positive charge moving the other direction. So as we talked about, and over here we have a model of electrons flowing. Well, if electrons are flowing this way, it's like a positive charge is moving the other direction. It doesn't matter which way you think about it. As a positive charge moving this way, a negative charge this way. By convention, we talk about a positive charge moving the other direction. Okay? That's just how we roll. So the I stands for intensity. It's the current. It's the intensity of the flow of current through a circuit. And there's a schematic diagram with a switch, a battery, a light bulb, and electron flow is this way, but conventional current is exactly the opposite direction, and you can control that with your switch. All right, two kinds of current. You got your direct current, you got your alternating current. You got your DC goes in one direction. So out of this battery, electrons are going this way, or positive current's going this way, and it doesn't change. But in an AC current, like you have a generator, you have a spinning magnet, we'll get an induction in another unit, in our last unit, and how that works and everything. But what happens is, as the magnet, the wire spins in a magnet, it pushes current in one way, then pulls it back the other way. So you get a push and a pull, push and a pull, push and a pull. The current goes one way, then the other way, one way, then the other way. In fact, your lights right now, especially if you have, well, your fluorescent type, but any of your lights, they're not on all the time. They actually go on and they go off, and they go the other direction, then they go off, they go on and they go off, and so on. But it happens so quickly you don't even notice. This takes a 60th of a second to do one whole cycle on the AC in America. You go somewhere else like Europe, they do things a little slower. They're not as fast as we are. I guess they're not, I don't know. But it's 50 hertz over there. So Ohm's law. So we learned about Ohm's law. It's the relationship between potential, the flow of current, and the resistance. So if you we did an experiment on people. We found out as we increase the voltage across people, you have an increase in current. Well, that means this slope is actually gonna continue on. Now, if it's an ohmic device, ohmic means it's a constant resistance. That if you double the voltage, you double the current, and it's a constant resistance. So that's what we're really generally talking about, things that are ohmic. Now, when you guys do your little lab with your FET stuff, That's going to be ohmic. In reality, if you used real light bulbs that had a filament, the more current, the hotter they are, they actually have a greater resistance. So it's not really a straight line. But for ohms law, we're talking about things that are ohmic that have a constant resistance. So resistance is the restriction of flow of charges through something. And normally what we would use is little tiny filaments of wire inside a light bulb, and it gets really hot. All this current goes through this tiny little light bulb, and it gives off a lot of light. Okay, that's generally how that works. But because of the thickness of this wire, the thinner it is, the more resistive it is. If the material is not as good of a conductor, it's a better resistor. Or the other thing is the length. The longer this thing is, the more resistance there is. And it's measured in ohms, which is a Greek thing, running out of American letters there. It's using a horseshoe for resistance. All right, so electrical power, you got your generator at the power plant over there. Then it steps up the voltage to really high voltage, and then it comes to a power substation, drops it back down for a lower voltage, and even finally by the time it gets to here, drops it down to 120 at your house. There's reason for going to really high voltage here, which we'll get into it another time. High voltage means you have a lower current, and there's less heat loss because you're heating less current flowing in the wires. The energy is transferred by high potential, not a high current, which would lose a lot of energy through warming the wires. Alrighty, so power. So power is your energy per time. So to find your work or energy, that would be your volts times the charge. I know it's not in this picture right over here, but it's your volts times your charge is your energy. We'll divide that by time, your energy per time. That's what power is. But it turns out this is your charge per second. So if you already have your voltage, take it times your charge per the time, or just voltage times the current, that is the easiest way to find your power. So power is the rate of doing electrical work, which is easily found by your voltage times your current. Okay, so if you use Ohm's law, you substitute in like the V, you put an IR in for that, you get an I squared R. Or if you substitute for the I, the V squared over R, you get a V squared over R. So there's several different formulas that find the exact same thing. They're all derived from this, the power, the volts times the flow of current. Which if you did mechanical power, if you remember that, that's your force times how fast something moves. So it's similar, but that's mechanical, not electrical. Okay? All right, so here we go. We have our parallel or series circuit. Which is it? It's both. So you got your series over here, you got your parallel over here. They work differently. So these are two basic ones. Yes, you can mix and match series. They come one right after the other. That's why they're in a series called the Wilde series. So there's a little wire here. If it's an incandescent bulb, it goes in one direction, then comes back out the other side. Okay, so it's not really that magical. And in parallel, you have three different paths you can take in this picture. So schematic symbols. This is for your battery. This is for your voltmeter. There's your ammeter. There's your switch. There's your battery. Alongside is a positive. There's your light bulb with your tiny little thing in there. So the voltmeter measures the electric pressure. Ammeter measures the flow of current. They are hooked up differently. We'll get into that in a moment here. I know we're flying. So this is a typical schematic diagram. You notice you want to measure the flow of current. It has to be in the system. Every charge has to be counted going through this ammeter. It has to be hooked up in a series. Now this has very low resistance. If it didn't have very low resistance, that would change the flow of your whole circuit. So it's got almost no resistance, but that's why you put it in a series. It's counting all the charges going through. This voltage measures the pressure on one side compared to the electric pressure on the other. How does that pressure compare? So if this was a fluid flowing through here, this would be a pressure meter showing how the pressure is, how much higher it is here than this side. Well, this being a voltmeter, it's comparing the higher electric potential here to the lower electric potential over here, but it's measured in parallel across what you're measuring. There's virtually no flow through a voltmeter. It's just measuring the pressure. All the charges would go through the resistor. You're just measuring the pressure on one side to the pressure on the other. And a rheostat is a variable resistor. That means you go higher or lower, which makes the current go larger or smaller, depending on which way you're turning the rheostat. Okay? All right. Read that stuff in another time. Simple circuit. You got your battery, got your wire, got your bulb. on the lab you guys are going to do, if you choose to do so, you can do a series and you're going to do a parallel. It doesn't have to look exactly like this. This is just one way to hook it up. You can put your switch in there if you want to. If you want to put a switch in, whatever you choose. Okay? So there's your series. That's the same in the series. Do you remember? It's the flow. Awesome job. So you have to have the same flow everywhere in here because there's only one path. It's the law of conservation of charge. We're not really storing any charge up anywhere. You have to have the same flow here as you have here as you here. It's the same flow everywhere. But there's an energy drop. You're going to drop in energy. And the best way to measure the energy, no, voltage is not energy, it's energy per charge. It's the best way to measure how much energy we're losing. It's your energy per charge that you're losing as you go through each one of those. Those have to be summed up to find the total. Okay? Now resistances couldn't be easier on the series circuit. You just add them up. Because the more things you have in a row, the harder it is for that stuff to flow. It doesn't get easier, it gets harder. So you just add these all up together, and that's your total resistance if everything is in a series. But remember, the flow of current has to be the same. You only have one path. Okay? But the potential difference, if these are the same resistors, that would be the same potential difference. But if they're not, they're going to be different drops depending on which one is harder to go through. The hardest one to go through is going to have the greatest energy drop because it's the greatest difference in electromotive force or pressure across the thing. Okay? So, I know you love math, so here we go. That's the total resistance. You just add them up. 1 plus 3 plus 2, 6. Okay? Total current. Well, now you're doing Ohm's law. That's 12 volts divided by the 6 ohms. 12 divided by 6 is 2. There you go. What is the current through each resistor? 2, because it's the same every single spot. So if you have a greater resistance here, that slows it down not only here, but it slows it down here. It slows it down everywhere. Okay? Just like water, if you have only a trickle coming out of a little dam or a little pipe here, that means you only have a trickle coming into the pipe and a trickle leaving. That's only a trickle going into your pump. Got to be the same flow everywhere. But the voltage drop is another story. They're all three different ones. Pop quiz, which do you think I'll have the greatest energy drop? The 2, the 3, or the 1? It's the 3, of course. It's the hardest to get through. You're going to have the greatest voltage drop across that one. This is the easiest one to get to. You have this least voltage drop. If you did this experiment in reality, even the wire has some resistance. There's a small voltage drop from here to right over to here. Not a large one, but there's still a drop because there is some resistance there, just not much. So you got to do all three of them. Okay? So just as predicted, the one with the highest resistance, the 3, V equals I times R, is the greatest voltage drop. And if I take 4 plus 6 plus 2, what do you get? Awesome, 12. Because they sum up to be what the potential difference is there. So that's your series hookup. So they all add up to the total of 12. Okay, let's try some parallel stuff. The math gets a little crazy on the oh, we're not ready for that yet. We're talking about a little Kirchhoff voltage law here, summing up potentials going around there. So what that means, if I have 12 volts here, it's going to drop some here, it's going to drop some more here, then this adds up to whatever it's dropped. So if I get a plus 12 on the battery, I might get a minus 6 there, so I'm down to 6. Then a minus 6, I lost another 6, I'm back down to 0. Or maybe I lose, this is the higher resistance to this, and I go from 12 volts to 8. So I lost 4 there. That means I'm going to lose 8 across my last one. So what the battery does here is it oomps. It's like a pump, electron pump, that gets the potential high, whatever this amount is of the battery, the EMF, and then it's going to drop. It's going to drop over the first one. It's going to drop over the second one. And so which one of these two is a higher resistor? Pop quiz. Which one is a higher resistor? It's number 2 because you lose a lot more energy getting across that thing. But the point is it goes back to 0 until it comes back to the battery down. The battery pumps it right back up to the 12. So when we sum up any loop, it's going to always sum to 0. The potentials will always sum. The battery's a plus. The resistors will be minuses. Okay? All right, here we go. So in the series, basically we start off with the total. We have a drop across one resistor, drop across the other. That all sums up to 0. Okay? So your total voltage drop across everything. But we're going to get a separate PowerPoint just on the Kirchhoff thing because it's going to take some practice, more practice than we're going to spend running through this little thing. Okay. Hey, now it's time for the parallel circuit. So what happens to the current? You notice we have 3 different branches.